Welcome to this comprehensive training video on Snowflake Cortex fine-tuning. We will explore how this powerful feature enables secure customization of large language models using your proprietary data inside a Snowflake. Let's get started with the foundational concepts. Cortex fine-tuning is an important feature available within the comprehensive Snowflake Cortex AI suite. Its primary purpose is to allow users to effectively customize or specialize existing large language models. This process utilizes advanced parameter-efficient fine-tuning, often referred to as PEFT, which allows for the creation of lightweight adapters. These adapters efficiently adjust the behavior of massive, pre-trained models to perform significantly better on highly specialized, narrow tasks that are unique to your business domain. Crucially, this entire service is managed entirely by Snowflake. This means you can execute the complex fine-tuning process directly on your own proprietary data securely within the Snowflake environment, eliminating complex infrastructure management and data movement risks. The fundamental goal of this approach is to markedly enhance the model's overall performance, particularly its knowledge base regarding specific domain terminology and unique business tasks. Fine-tuning provides superior results compared to using a generic model without needing the extensive investment required to train a large model completely from scratch using raw data and compute power. Accessing and utilizing this powerful capability is strictly controlled and governed by specific Snowflake database roles and prerequisites, ensuring enterprise-grade security and compliance throughout the data lifecycle, ensuring data remains safe. We learned that Cortex fine-tuning is a fully managed service that uses PEFT to create customized LLM adapters based on your proprietary data, improving performance on specialized tasks securely within Snowflake. This diagram shows the basic flow of how Cortex fine-tuning creates a specialized model from a generic one. We start with a large, pre-trained LLM, which serves as the foundational model providing generalized knowledge. This model is then subjected to the parameter-efficient fine-tuning, or PEFT, technique, which efficiently adjusts the model's weights using specific, targeted data. The required training data, consisting of input-output pairs reflecting your desired behavior, is securely hosted within Snowflake. This entire process is managed by the Cortex fine-tuning service, which orchestrates the complex compute required for adaptation. The outcome is a lightweight customized LLM adapter. Understanding when to leverage Cortex fine-tuning is key to optimizing your AI investment and achieving the desired results. You should consider fine-tuning as a powerful alternative solution when standard AI techniques, such as basic prompt engineering or sophisticated retrieval-augmented generation, prove demonstrably insufficient in consistently delivering the required level of task accuracy or desired specialized output quality. Simple prompt engineering often struggles when the task involves highly complex, technical jargon that the base model has never been exposed to during its massive general training phase, or when the output absolutely must adhere rigidly to specific, non-standard formatting rules, like proprietary XML output. While retrieval-augmented generation, or RAG, excels at retrieving relevant facts and information, making it strong for factual grounding, it may frequently fall short if the use case requires the resulting output to possess a very specific style, maintain a particular professional or brand-aligned tone, or exhibit complex, consistent conversational behavior beyond simple factual recall, demanding a nuanced model. Critically, opting for fine-tuning provides substantial savings in both monetary cost and development time when compared directly against the prohibitively expensive and technically complex endeavor of attempting to train a new, massive language model completely from scratch using raw data and compute power. Therefore, this managed service is uniquely ideal for any highly demanding enterprise task that rigorously requires consistent, perfectly repeatable, and highly specialized output that demonstrates a deep and accurate assimilation of internal domain-specific language and proprietary business logic. We established that fine-tuning is used when prompt engineering or RAG fail to deliver the required specialized accuracy, tone, or complex behavior. It is a strategic middle ground, avoiding the massive cost of training from scratch. This Venn diagram places Cortex fine-tuning within the spectrum of LLM solution strategies, clarifying its optimal use case. We have prompt engineering, which uses clever instructions to guide a generic model, and retrieval augmented generation, or RAG, which provides external facts for grounding answers. The overlap between prompt engineering and RAG often addresses factual question answering, where information is retrieved and summarized. The operational workflow for Cortex fine-tuning starts directly within Snowflake by executing a specialized structured query language function. This function is named snowflake.cortex.finetune, and you initiate the process by passing the explicit create command as its first primary argument, signaling the start of a new training job. This critical function requires several key parameters for successful configuration, including a unique name for your resulting custom model, the identifier of the chosen base large language model, for example, Mistral 7b, and crucially, the specific SQL queries that define both your meticulously prepared training and validation datasets. It is an absolute requirement that all the source training data must be securely contained and readily accessible within an existing Snowflake table or a view, ensuring maximum security and eliminating unnecessary data export. The results returned by the mandatory training data queries must strictly contain exactly 2 columns, which must be precisely named prompt and completion. The prompt column holds the specific input text the model receives, while the completion column contains the exact desired response text that you want the model to generate based on that prompt, effectively teaching the model its new behavior. The core mechanism involves repeatedly exposing the model to thousands of these meticulously crafted prompt and completion pairs, systematically adjusting its internal parameters until its responses closely align with your defined desired output behavior. A critical operational detail is that these fine-tuning jobs are designed to be long-running processes. They successfully initiate and then operate completely independently of the specific worksheet session from which they were initially launched, ensuring robust execution. We learned that fine-tuning jobs are launched using the snowflake.cortex.finetune create function. The data source must be a Snowflake table, view, and must provide columns explicitly named prompt and completion for supervised training. This sequence diagram visualizes the steps involved in launching a fine-tuning job. The process starts with the user or developer initiating the fine-tuning process from their Snowflake session by calling the specialized fine-tune create function, along with defining the parameters and the necessary SQL query. Cortex fine-tuning offers a selection of capable open-source base models upon which you can build your specialized adapters. These available foundational models include powerful options such as Meta's widely recognized Llama 3 and Llama 3.1 families, alongside the high-performance models originating from Mistral AI, providing a diverse range of capabilities for various enterprise needs. Specifically, common base models available for fine-tuning include the effective Llama 3.8b model, the highly performant Llama 3.170b, and the capable Mixture of Experts model, Mixtral 8x7b. When preparing your data, you must be acutely aware that every single base model imposes a strict limitation on its internal context window size. This crucial constraint restricts the total maximum size, measured in processing tokens, of the input prompt and the desired completion output combined together for every training example you provide to the model during the learning phase. Furthermore, Snowflake imposes explicit limitations on the maximum effective row count that is permissible for use during a training job. This hard limit is mathematically influenced by the specific capabilities of the base model you select and the predetermined number of training epochs defined for the job. You must know that the default fine-tuning process is configured to run for exactly 3 epochs. This default setting is critical because you must factor this number into your calculations when determining the maximum volume of training data rows that your chosen model can successfully and efficiently utilize within the given resource constraints, ensuring optimal performance. We learned that models like Llama 3 and Mistral AI are available for fine-tuning. The crucial constraints are the context window size for the prompt, completion pair, and the effective row count limit, which is affected by the 3-epoch default. This quadrant chart maps some available base models for fine-tuning based on their computational requirements and context window size. Models that fall in the lower left, such as Mistral 7b, generally offer lower cost and smaller context windows, making them suitable for simpler, shorter tasks. As we move right, models like Llama 3.18b offer a larger context window, enabling them to process longer prompt and completion pairs, while maintaining moderate compute costs. In the upper right quadrant, models like Llama 3, after the potentially long-running training job successfully completes, your newly specialized fine-tuned model becomes instantly available for immediate use in live inference scenarios. You can deploy this custom model directly by invoking the standard Cortex Complete Large Language Model function. Crucially, the unique name that you originally defined for your model during the initial create command is now used as the specific model identifier within the complete function call, directing the system to use your customized adapter. For enhanced management visibility, fine-tuned LLMs are automatically displayed unlisted within the intuitive Snowflake Model Registry user interface. This central location helps manage your full suite of machine learning assets, appearing seamlessly alongside traditional ML models and other custom AI models, such as those from Document AI. However, a significant operational distinction exists. While they are viewable in the UI, these Cortex fine-tuned LLMs are specifically not managed or controlled using the Model Registry's programmatic API, so model lifecycle operations must be performed using the dedicated fine-tune function commands. For broader enterprise use, these specialized fine-tuned models can be securely shared with other Snowflake accounts or departments by leveraging Snowflake's robust native data sharing mechanism, requiring the consumer to be granted the appropriate usage privilege on the object. A final critical point concerns deployment across geographies. If you require model inference to occur in a different cloud region than where it was originally trained, you must explicitly replicate the model using standard database replication because Cortex fine-tuning does not support automatic cross-region inference for these custom models. We learned that fine-tuned models are used for inference via the complete function and are visible in the model registry UI. For multi-region deployment, database replication is mandatory because cross-region inference is not supported for fine-tuned models. This diagram details how the fine-tuned model is consumed and managed. The user or application makes an inference call directly to the complete function, specifying the fine-tuned model's name. The request routes to the fine-tuned model adapter, which works in conjunction with the massive, generalized base LLM to generate the specialized response efficiently. Effective cost management for Cortex fine-tuning relies on understanding the two distinct billing components. The cost associated with the initial training process is based exclusively on the volume of trained tokens. This metric is calculated by precisely multiplying the total number of input tokens used in your training data by the specific number of training epochs you defined for the job, providing a clear formula for budgeting. Separate from the training cost, every subsequent inference call made using the resulting fine-tuned model incurs additional compute costs. These ongoing inference costs are accurately measured based on the cumulative number of tokens processed by the AI_complete or complete function during each model invocation. For auditing and managing these expenditures effectively, administrators should meticulously query the Cortex_fine_tuning_usage_history view, which is readily available within the account_usage schema, offering detailed breakdowns of credit and token consumption specific to fine-tuning jobs. Regarding strict governance and access control, initiating a fine-tuning job requires the invoking user's role to possess the fundamental Snowflake.Cortex_user database role. Furthermore, to successfully save and register the resulting fine-tuned model object, the role must also be explicitly granted the create model privilege, or full ownership, on the designated schema where the new model is intended to be stored permanently. Once successfully created and logged, fine-tuned models are categorized internally as Cortex_fine-tuned type objects, ensuring they are treated with the same high level of governance and security as other critical schema-level machine learning assets within the Snowflake platform. We learned that training cost is based on trained tokens epochs, and is monitored via Cortex_fine_tuning_usage_history. Governance requires the Cortex_user role and create model privilege on the schema. This Sankey diagram illustrates the dual flow of cost and the necessary governance steps for Cortex fine-tuning. The costs originate from two streams: the initial training data and prompts, which incur the fine-tuning cost based on tokens multiplied by epochs, and the inference cost, incurred later when the model is actively used to generate completions. Both cost types are consolidated and tracked in the Cortex_fine_tuning_usage_history view, which is the primary source for monitoring expenditures.